Swayam Prabha. Digital India. Educated India.
Hello everyone. Now we will start a new topic which is differential gear in roving frame. So, differential gear or epicyclic gear we have discussed in comber, and in comber the differential gear is used in detaching roller movement, but here the differential gear is used mainly for the bobbin's RPM, bobbin speed control. So, from the differential gear the speed goes to the bobbins, because bobbin needs motion which is actually it is a variable motion and also some constant motion. So, two motions are actually superimposed. Constant motion basically come from the main shaft, and differential that variable motion comes from the cone drum system, and it directly it is added upon and gives the to the bobbin speed. So, why these things we will discuss here. Okay. And along with this we will also discuss here the cone drum speed, cone drum motion, that we will discuss here, how the bobbin speed is related with the cone drum speed. This part also we will cover here. So, bobbin drive if we see in particularly we will discuss here in bobbin leading mechanism. So, cone drum change wheel is there K. So, you will see that this is the cone drum change wheel. So, this is the typical drive mechanism of LR machine, retar machine also. If the tube diameter is altered, so here the tube diameter means your bobbin diameter, there are different bobbin supplier. So, there it is not that standard diameter is not there, but it may change a little bit. If the bobbin empty bobbin diameter changes, the starting speed of bobbin must be adapted. So, starting speed also changes. So, that if it does not match, then there will be breakage, because the winding speed will be different. So, that will get the system will get disturbed, and to alter this we have to change the K value, that is cone drum change wheel. The ratchet wheel has not been operated at this stage, because at the ratchet wheel only operates after one layer. So, for on the bobbin, empty bobbin, ratchet wheel has not been operated. So, cone drum's belt, cone belt has not shifted, started shifting. So, when in the first layer, so all these problems will be there, because from the second layer onward we can have all these systems in place. Ratchet wheel will be activated and cone drum belt will shift, but in the first layer nothing has happened. So, starting position of cone belt may be changed. So, we can change the starting position of cone belt to adapt to actually adapt the change of the bobbin size, or we can change, we can do it in, if we do not want to shift the cone belt in the first stage manually, we can change the this change wheel K. A ratchet change wheel is there, that is ratchet change wheel, here ratchet change wheel, and ratchet change wheel actually changes the rate of shifting of belt, that we will discuss separately. Determines the amount of belt shift, depends on the increase in bobbin diameter. Okay. That is how much increase is there, that we can change. because bobbin diameter, if it is more, then we have to change the speed in rapidly. So, that accordingly the ratchet wheel number of teeth we have to change. Okay. Now, bobbin diameter, if it increases, the bobbin RPM will reduce. That is a bobbin leading mechanism we have already discussed. Variation in bobbin speed, it originates from cone drum. That cone drum actually is the originating point of the bobbin speed variation. Here we can see the top cone drum, which is getting drive directly from the main shaft, rotates at constant speed, but the bottom cone drum, its speed changes depending on the shifting of cone belt. So, in this system, the top cone drum, which is moving at constant speed, at the start point, this is at the maximum diameter, and whereas the bottom cone drum has with a minimum diameter. That means, the bottom cone drum is moving at maximum speed, and as it moves gradually towards right, the belt moves gradually towards right, the bottom cone drum speed gradually decreases, and this variation originates from this cone drum, and from this cone drum the speed, bottom cone drum speed goes to the bobbin through the epicyclic gear. This is the epicyclic gear system that we will discuss in detail, and builder motion shifts the cone belt. This is the shifts the cone belt, and continuously reducing the rotation rate of the bobbin. Now, the issue is that here it is the speed, we are getting variable speed here itself, and we can directly give this motion, variable motion, to the bobbin. So, why do we use differential arrangement? Why do we want to have superimposed additional motion of main shaft? That is the important question one may ask, because transmitted this speed transmitted via gearing to the differential arrangement and then superimposed with a constant speed of main shaft. The basic idea is that in the bobbin leading system, there is a reference speed. Reference speed is the speed of the spindle which is coming from the main shaft, and the speed has to be very high, higher than the spindle speed. So, to have that much high speed from the bottom cone drum will be difficult. So, we need one big roller and arrangement, and that in that case we may not be able to attain that speed which is required, higher speed. So, to have this arrangement, to have this condition met, what we need, we use one differential gear system, and there the two motions are going there. One is directly from the main shaft, which is constant motion, another is the variable motion, and they superimposed through the epicyclic gear system, and the output of this epicyclic gear system goes to the bobbin, but the spindle gets directly through the hollow shaft directly from the main shaft, which is getting constant motion. So, resultant movement to the bobbin drive. So, that is how we get the higher speed. Now, if you see here, the arrangement of the epicyclic gear, you can see we have a constant speed which directly comes from the main shaft, green color, it shows in green color one constant motion, and then this is the constant motion, it goes to spindle, that is a flare also. Another is variable motion which is shown in the red color, and this variable motion, this is coming from the bottom cone drum, and these two motions are superimposed and we get which is the blue color output, which is through the differential gear arrangement, and this variable motion goes to the bobbin. This is the hollow shaft and it gives drive to the bobbin driving roller 80 teeth, and from there the drive goes to the bobbin. And here this shaft is the hollow shaft, and through the center the main shaft goes, which drives the one side, it is driving the spindle, other side it drives the drafting system as well as the top cone drum, which rotates at, which moves at constant RPM. Now, the same method, velocity ratio method we will be using. So, the tabular velocity ratio calculation, the three methods, tabular method, formula method, instant center method or tangential velocity method. So, we will be adopting the tabular method here, the same basic contents we have already discussed in the comber section. Here three components, basic components are required, and the animation here, the same animation which we have shown in the comber, you can see once again. So, where you will see that the A as a sun gear, B planet, and this is C arm, C is arm, and there in that you will see the three types of motions are there. One is the 1 degree of freedom, 2 degrees of freedom and 3 degrees of freedom. So, you can see here, and this tabular method determines the motion of every element in the gear, and two easily describable parts of the total motion are analyzed separately and then added together, that we have discussed in the comber also. Motion of all components are rigidly fixed to the rotating arm, and motion of all the components are relative to the arm. Okay. Now, here you can see whole systems are locked and the arm is rotating. So, other systems, other components will be rotating. So, we are giving the speed plus y, and then arm is locked. The whole system is locked earlier, arm was revolving, now arm is locked. So, arm speed is 0, and then rest other components will work as a normal gearing system. So, x is the speed of the, x speed is given to the sun gear A, and B will rotate as in the other direction, negative direction, minus x by Z A by Z B, and then we are adding it to. So, plus y, and sun gear will rotate y plus x, and planet gear B will rotate y minus x by x multiplied by Z A by Z B. So, these two are added, these two rows are added. Now, sun gear is fixed, that is N A is fixed, y plus x is 0 equal to 0. So, arm C revolves at plus 30 rpm. So, N C is 30, N C is nothing but y, we have seen in the earlier table. So, x will be minus 30. RPM of planetary gear B is given by 30 minus. So, what we have seen, you can go back here, y minus x multiplied by z a by z b. So, we can get using this y, this is a and z a by z b, and z a z b if we know 80 and 40, then we can calculate N b is 90. The same thing we have seen in the Comber section also. Now, here we are just reproducing the same table here. Now, N b is calculated. So, N b we can see here as 90. Now, planetary gear train is to make use of 2 degrees of freedom of mechanism, while the sun gear is released from the ground. This mechanism is 2 input systems, okay, and to determine the complete motion of the gear, 2 separate inputs are given, they are combined to give an output speed which is proportional to the sum or difference of 2 inputs. This may be in the addition or maybe subtraction depending on the direction of motions. Now, we can see here, if the RPM of sun gear is 120, then Na, that is Na will be 120. Sun gear means it is a x plus y using the tabular method. So, x plus y is 120. Now, the RPM of arm C is plus 30. Let us see it is moving at plus 30 RPM. So, y will be, this is y will be 30 and x will be plus 90. So, RPM of planetary gear will be y minus x by z a by z b. So, it will be minus 150. So, we can see if sun gear is rotating in plus direction and this arm is rotating in plus direction, we will get the rotation in the minus direction, that is a negative direction, opposite direction at 150 rpm. So, if the sun gear is in the negative direction minus 120, then x will be minus 150, because N c is 30, that is y is 30. So, it will be minus 150 in that case. So, only thing is that here sun gear has changed its direction. It is rotating at 120 rpm, but it is changed in the opposite direction. In that case, the impact will be, you can see that the planet gear will rotate at 330 rpm in the positive direction. So, what we have seen, the changes in direction or magnitude will greatly affect the output speed. So, this is the table. Now, coming to the roving system, roving machine, the combined fixed speed related to flare speed with a variable speed related to bottom cone drum speed, okay, gets the bobbin speed. So, actually these are combined and they are used to have the combined speed in the bobbin. Rotational speed of winding reduces from bare bobbin or empty bobbin to full bobbin, that we have seen in the last session through the numerical calculation. So, it gradually reduces. The speed reduction is carried out using a pair of cone drum, cone pulleys and belt shifting mechanism, that. So, gradually the belt shifts. So, we get the speed reduction. So, variable speed is given to the epicyclic gear. So, this variable speed which we are getting from the bottom cone drum, it is given to the epicyclic gear, and it is superimposed with the fixed speed from the main shaft. We can see here from this diagram, we can see this is the bottom cone drum, top cone drum. Top cone drum gets the constant speed, but bottom cone drum, as it is belt shifts, it speed varies, and from this bottom cone drum the speed goes to the pulley 50 with the 50 teeth, and here this 50 teeth pulley, it gets the variable motion from the bottom cone drum through the gearing diagram, and here it is a hollow system, and with this arrangement this 50 acts as a arm which revolves the epicyclic gear train, that is there is a 50 and 25 and 28 teeth rollers. Those are actually the planets around the sun, which is 59 teeth, and this 59 teeth sun gear is fitted firmly on the main shaft, which rotates at main shaft speed. So, this is the constant speed getting from the main shaft, and the variable speed which is at the 50 teeth roller, which is getting the variable speed from the bottom cone drum, and these two speeds are superimposed, and finally it gives the output roller 62 teeth, which rotates at the which is the output of the epicyclic gear, and ultimately it drives the bobbin through the hollow shaft. Hollow shaft, the 62 is attached with the only the hollow shaft, and it is freely rotating, it can freely move over the main shaft. It has nothing to do with the main shaft speed, but 59 is the sun roller, sun gear, which revolves at the main shaft speed. So, this hollow shaft is connected with the roller 81, which rotates at the speed of the output of the epicyclic gear 62 teeth, and from 82 the 81 teeth this gear, the bobbin gets motion, whereas the spindle directly gets motion from through the 102, and then it is going through the to the 80 teeth, and from there directly to spindle. So, these are the two motions here. So, here that is why this system is known as arm system, because arm, the function of arm, as I have mentioned, this is the component which makes the planet revolves around the sun. So, that is why it is arm. The velocity of fiber strand delivered by the front drafting roller is V. This is the front drafting roller, the velocity is V, and rotational rate in RPM, bobbin RPM is NB, and flare RPM is NF. And what is winding RPM? Winding RPM is effective winding RPM at particular bobbin diameter, which is NB minus NF. So, winding RPM at NB minus NF. So, NB we can calculate NF plus NW. So, winding RPM. So, rate of winding, that is meter per minute, must match with the delivery speed. So, whatever we are delivering, that winding speed has to be matched, that we have seen through the numerical earlier. If the bobbin diameter in millimeter is dBm for mth layer, dBm bobbin diameter. So, NW winding RPM means NB minus NF, as we have seen, NB minus NF equal to 100 V, V is in meter per minute, and pi dm, dBm, dBm is in millimeter. So, here it comes meter. So, that we have already seen that the relationship V equal to pi dB NB minus NF. So, NB minus NF is NW. So, NW will be so this is NW. So, NW is equal to V by pi dB. This 1000 is only for the conversion from meter to millimeter to meter, that we have already discussed. So, here we can see this is the relationship, it comes from this relationship. Now, diameter of bobbin dBm increases from dB0 to dBf, the initial diameter to final diameter, that is empty bobbin to the full bobbin respectively. dB0 is the empty bobbin, dBf is the final bobbin, full bobbin. M is the winding of mth layer, okay, of the roving on the bobbin. T is the thickness of the bobbin. Okay. If these things are there, then we can get the dBm. So, this is, suppose this is a empty bobbin for first layer. So, if we draw the first layer and if we consider there is no compression, if the thickness or diameter of the bobbin is the thickness or diameter of the roving is T, okay. T is the thickness, means roving thickness or diameter. So, what will happen for bare bobbin is dB0, okay. For first layer what will happen? Diameter will be dB0 plus T into 2. So, dB0 it will be dB0 plus 2T. This is for the first layer. Second layer it will be changing. So, it will be effectively in generalized form will be dB0 plus 2 mth layer minus 1 into T. For first layer that will be, it will be 0. So, second layer, for second layer the diameter will be, you just put it as a 2, that means dB0 plus 2T. This is for second layer. For third layer it will keep on changing. So, this is the generalized formula for mth layer. Now, this is the total arrangement of the drive and here is the gearing arrangement of the epicyclic gearbox. So, we will use these things with the assumption this is arm. Now, here the front roller the front drafting roller diameter we will assume as 27 millimeter. So, this is the real data has been taken. So, front roller drafting roller diameter and which gets drive from the main shaft, that is 27 millimeter. We will try to actually get the front delivery speed and the winding speed, try to see the stretch or maybe relaxation, that we will try to calculate here. So, for that we need the delivery speed, front roller delivery speed we have to calculate from the gearing diagram given. So, drafting roller diameter is 27 millimeter. The diameter of top and bottom pulley, cone pulley at the starting point is 216, this is 216 at the starting point millimeter and bottom pulley as 114 millimeter corresponding to bare bobbin diameter which is 48 millimeter. 48 millimeter is the bare bobbin but empty bobbin diameter, okay. And flare RPM is 1000 RPM, that is we have fixed, and main shaft speed is RPM is 827 RPM, 827 RPM. From there we can calculate the spindle speed, because this is the main shaft, this one is getting 102 roller is getting RPM 827, from there this is 80. So, from there we can get calculate, we can calculate here. So, we can calculate the NF flare speed E4 Nm, Nm is the main shaft speed, E4 is given 1.209. What is E4? E4 is the gear ratio between the main shaft to the flare spindle, main shaft to the spindle. So, if we know the main shaft speed, if we multiply it by the gear ratio, we will get the flare speed. So, if we multiply 827 multiplied by 1.209, we will get the flare speed, that is the gear ratio. Here is the 48 mm and flare speed is 1000 and main shaft speed is 827. RPM. E1. Now, the gear ratio, let us see the gear, different gear ratio we will consider. E1 is the gear ratio between bottom cone pulley to the gear 50 teeth. So, bottom cone pulley RPM to the 50 teeth, this gear ratio is E1, straightforward, that we can always get. E2 is the epicyclic gear. So, 59 to 62, between 59 to 62 this gear ratio is E2, this can also be calculated. E3 between output of the, that is epicyclic gear 62 to the bobbin. So, output of 62 means output of epicyclic gear 62 and 81 they are same from there to this point, this is E3, and E4 is the between the main shaft gear to the flare. So, this is to E4 which we have already seen, okay. That, so these are the constant we can calculate beforehand, okay. Now, concentrating on the gear ratio of the epicyclic gear. Just I have enlarged one. Now, this is the main shaft. Main shaft is connected with the this 50/90. Here it is called sun gear, which is rotating at constant speed of the main shaft, and this arm this is arm, and here it is also arm, because they are in the same hollow shaft. It gets variable motion from the bottom cone pulley and which revolves this wheels 28 and 25 around the sun, 28 around the sun. So, that means 28 is the planet and 28 and 25 they are in the same shaft, okay, and fixed, they are rotating, they rotate at same speed, and 25 gives the motion to 26, and 26 is fitted on hollow shaft. So, it has nothing to do with the main shaft motion, it gets only motion from the 25, this one. Now, try to see. Now, here as we have number of components increased, so we will see all the components. So, gear 50 teeth, this one is arm, gear 59, this one is sun gear, gear 28, this is planet, and 25 is actually same as 28, because they are in the same shaft fixed, and gear 62 is the output of the epicyclic gear. So, same tabular system treatment will be there. First, whole system is actually revolving, they are locked, they are revolving at the speed of the arm plus y. So, y we are giving to all the components. Next is the arm is locked. So, arm we are locking, only the motion is given by the main shaft, that is the sun is rotating, sun is moving at x speed. So, arm is locked. Now, when sun is rotating at plus x speed, so gear 28 will rotate, that is planet will rotate on the other direction minus x multiplied by 59 by 28, that is the teeth ratio. The same speed will be taken by the 25 teeth, and the 25 teeth will give the motion to the gear 62 with this ratio, okay. And this one is actually nothing but the epicyclic gear ratio, as we have seen. I think it is a that we will see, okay. Now, if we add, it is y plus x minus this will become 2.11 x plus y, and next is the minus, same it will be there 2.10, that is 2.11 y, same value, and from there we get 0.85 x y. Say 0.85 is the gear ratio, epicyclic gear ratio. Now, RPM of main shaft or 59 teeth, that is the sun gear, is 827. This is that we know, we have already seen, it is 827 is given. Now, that is what is that 59 teeth, the sun gear is nothing but x plus y is 827. RPM of gear 50 teeth, 50 T, that is arm is y. So, what is y? Y we can calculate from the this gearing ratio. So, 820 I will just show you how are we getting this value. This is main shaft gives drive to the 102. So, 102 is getting drive, it gives drive to the this is rotate 102 is rotating at the main shaft speed 827 and it is giving drive to 62 teeth. So, 102 by 62, then 32 by 70, 32 by 70, then that is the speed which is going to the top cone pulley is rotating in this speed, and then 216 is the this diameter of the top cone pulley at the starting point, and 114 is the diameter of the bottom pulley at the starting point, that we have already seen. So, this is top and bottom cone pulley at the starting point 216 and 114 mm. So, that we have already seen here 216, 114, and then it has then 27 and 50, 27 and 50. So, that is why we are getting the at the starting point bare bobbin the speed of the arm is 636, that is y. Therefore, x will be 827 minus 636, so 191, that is x. So, RPM of 62 teeth. So, RPM of 62 teeth, that is output, will be 0.85, which is the epicyclic gear ratio multiplied by x plus y. So, we can calculate this. So, this will become 798. 798 is the speed of the this gear 62 output, and from there if we know the gear ratio from the output of the epicyclic gear to the bobbin. So, this is actually E3, that is epicyclic gear ratio plus from epicyclic gear output to the bobbin. What is that? That 81, that is 62 speed and 81 speed are same. So, 81 divided by 54 and here 36 by 38. So, we are getting the bobbin RPM 1134 at the starting point, okay, at the starting of the bobbin or at the bare bobbin. So, take up speed will be, take up speed is that pi 130, that is a, what is 134? NB minus NF, NF is 1000, we have seen already. So, 1134 minus 1000 becomes 134. So, pi d is the diameter, diameter of bare bobbin is 48. So, 48 millimeter diameter. So, we are converting. So, this is meter. Now, pi d NB minus NS, NF. So, NB minus NF is 134. So, that is how we are getting the take up speed as 20.42 meter per minute. So, this is the take up speed of the bobbin at the starting point. Now, let us see the what is the delivery speed. The delivery speed it is a fixed, so that we can calculate what is the delivery speed will be there. So, this is the from the main shaft speed directly knowing the gearing ratio and the diameter. Diameter we also have discussed. .27 millimeter and we can calculate the RPM. So, this is from there. Now, delivery rate is pi d, and what is the RPM of the delivery roller, which we get from the this main shaft 102, 64, 62, 70, 62, 70, 32, 70, and then 26, 67, 26, 67. From there we can get the delivery rate. So, delivery rate is given 20.47, and we have already calculated the take up speed. So, take up speed was just a minute, 20.47, and take up speed was 20.42. So, that is the take up speed by the bobbin, and delivery speed by the this 20.47. So, changing the number of teeth on the twist change wheel position B, C and D gears, what they will do? They will change the speed of the both delivery and winding rate. So, delivery and winding rate will be changed in the same proportion. Okay. This do not alter the roving slackness or stretch. So, here the roving will be little bit slack. So, which we normally keep, because delivery speed is 20.47 and the winding speed is, I will show you, 20.42. So, 20.42 is the winding speed. Here the winding speed by the means 20.42 meter per minute, okay, but delivery speed is 20.47. That is what normally we keep, because of the contraction, little bit contraction is there. So, accordingly we can, otherwise there will be stretch. So, these are the gear ratios as we have already discussed. So, from this derivation what we have learned, that we can calculate the speed of bobbin using the gearing ratio, or that is epicyclic gear ratio at any instant. Now, take up speed is 20.42 and delivery speed 20.47. So, roving slackness becomes 0.244%, that is typically close to the that is a contraction percent. Okay. Now, here what we have we can now calculate the bobbin speed at any position, position of the cone belt, and here the that we can calculate. Now, in the next session we will try to see how this cone belt, cone pulley, bottom cone pulley, top cone pulley is RPM is constant, that we can calculate from the main shaft speed, but bottom cone pulley is variable depending on the position of the belt. So, bottom cone pulley is RPM is related with the bobbin speed. So, how are this related? So, depending on the roving diameter and all this roving diameter. So, we can change the shift rate of shift. So, how are this first related, that we will discuss in the next session. So, relation between the bobbin speed and the cone bottom cone speed, that relationship we will discuss in the next session. Till then, thank you.